Yay. I will begin. Dear Father, we thank you for this day. I thank you for these students. Just pray you'd bless this class today. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so well, you can't see it, so it's fine. So I want to talk about basically applications of the gradient vector field to geometry. But what I'm really talking about today is, okay, so we've been looking at a function of two variables, right? F of x, y, or perhaps the function of three variables, f of x, y, z. And we've been calculating the rate of change of that function at a given point in terms of the directional derivative, right? And we've talked about how you can have a maximum rate of change, a minimum rate of change. If you choose u hat to be perpendicular to, and basically this is mostly what I've said the last couple days, has been the directional derivative in the u hat direction of f, right? At the point P, it's equal to the gradient of f at the point P, dotted with u hat, right? So this right here is the gradient of f at P, right? And I pointed out that this is a dot product of two vectors, right? So it's really just the magnitude of the gradient at the point P times the cosine of the angle between them, right? So if this is the gradient of f at P, and this is the point, the vector, the direction vector u hat, this is the angle between them, right? And the big idea that I shared with you guys is essentially just this, that minus the gradient of the function at the point is less than or equal to the directional derivative of f at the point P, and that is less than or equal to the magnitude. So this is the minimum rate, right? This is the maximum rate at which f changes at the point P in the direction u hat, right? You can see what, how do you make the max rate? Of course, this is what? Theta equal to 0. This would be what? Theta equals to pi, or 180 degrees if you're one of those people. So we can draw a picture of what's going on, right? If this is the point P, right, then if this is the gradient vector, if it points like that, right? So we have basically three cases, right? Like this way, this would be the maximum direction, right? If we go this way, that would result in being giving us the minimum rate of change for f at that point P. And what if we want the rate of change to be 0? Yeah, rate of change to be 0, we just go this way or that way, right? So this would be you could say the constant, for lack of a better notation. I say constant y because if we take, the gradient of f at the point P dot one of these constant choices, right? These, just my label, right? That's 0. So that means that the rate of change is 0, which means what? That means that the function's constant at that point P. If you go along, right, if you trace along this line, the function's constant along the line which contains those purple vectors. Right? Now all of this discussion, there's one thing about it, right? It's focused on a single point. Right? We're studying the change in the function of two or more variables at a single point. So now I'm going to turn the page and I'm going to start looking at the function more globally. Start looking at not just one point, but lots of points at once, right? And we do that through the study of what are called level curves. So let's talk about level curves. And I'll do that in contrast to, say, level curves versus graphs. All right? So when I understand a new concept, I always want to fit it to things I already know, right? I hope you do the same. A level curve, definition, C equal to, let's say, x comma y, such that f of x comma y equals to k is the level k curve for f of xy. You can also call, well, you know, in fact, a lot of times, guys, I don't use little f here. I tend to use a big F, actually. Let me do that. Big F. It doesn't, I mean, it's not, I mean, you could use whatever you want there. You could say Pac-Man of xy. It wouldn't make a difference, but I like to use big F. And so big F here is the level function. So this is the so-called level function. Right. So example. We'll keep it simple. I like this. This example is a pretty good one. What if we look at f of x comma y equal to, let's say, keep it really, really simple, x squared plus y squared. Right. So the level function x squared plus y squared, we can start looking at the level curves of this function, right? And we can graph those. So let's see here. Let me make myself a coordinate axis here. So here's my xy plane, right? And so I want to plot some choices, right? So we're looking at x squared plus y squared equals to k, right? Oh. Huh, interesting. Wow, that's a new mistake. Let's see here. I wonder what other new mistakes I'll make soon. Curious. Anyway, so x squared plus y squared equals to k. We're looking for the solution set to this equation, right? The solution set to that equation is the level curve. Right? So if you start thinking about it, you know, different cases here, if k is less than 0, what's the solution set? All right, so like k less than 0, no solutions, right? If we look at k equals to 0, what's that give us? X squared plus y squared equals to 0. What's the solution to that? X and y both 0, right? So that is just the origin. There's the level 0 curve. Level curve could just be a point, as my definition is stated. And then the more exciting thing, of course, which is what? When we have k positive, right? And if k is positive, we could rewrite it so k is equal to r squared, right? For some r. And the reason I write that is because then, I mean, you could say the square root of k is the radius, right? So if k is positive, we get circles, right? Those are supposed to be circles, right? And so maybe this is, let's see here. So we're looking at 0 is the center point, right? This would be 1, 4, 9, 16, assuming that that was, you know, 4, 3, 2, and 1 in the scale. What I'm trying to say is the 1, the 4, the 9, and the 16, these are k. Okay? because x squared plus y squared equals to 16 is a circle centered at the origin with radius 4, right? So how many level curves are there for x squared plus y squared? How can you, I mean, I've drawn 5 of them. There are infinitely many, right? So this picture is kind of like those, hey, like this. I found a use for the map. Woohoo! Well, kind of. Sadly, not very topographical, huh? Well, there's kind of some topographical stuff in here. You see these ridge lines, they should be like sort of equal. I don't know. I think it's just artistic, though. It's worthless. I had hope, but that dead, decaying map, it just serves to keep us from painting that part of the wall, I guess. I don't know. Maybe there's like is there a hole back there? Oh, sorry. Oh, okay, getting back to the story here. The point is, yes, I've drawn 5. These are just samples. Sample to illustrate the idea, right? You could draw as many as you need to illustrate what the contours look like. These, by the way, are called contours, aka contours for f. Well, contours for x squared plus y squared. Contour is just another term people like to use for level curves. So topographical map is based on giving you some sort of contour plot for what? Which function? The altitude function, right? The altitude function is what we use to make a contour plot. And that's usually called a topographical map, right? You get these lines of constant altitude. Those are constant level curves for the altitude function, yeah.
So we view contours and level curves as synonymous.
Yeah, contours and level curves are in fact synonymous here, yeah. Now, what other way did we have to look at the function f of x, x squared plus y squared? What else did we do in here already? Graph, right? How about the graph? What's the graphical viewpoint? There, I would look at z equal to, in this case, f of xy, right? And if you think about that, for this one, you could think about plotting the level curves down here, right? You could think about those level curves as lying in the xy plane, and you could think about you guys ever seen Stargate? Yes. Remember in Stargate the rings are like it's like that. So think of these as the rings on the ground, and so like the height is given by the level k. So this one lifts up to that. That one 2 up. This one's 3 up. This one's 4 up. Something like that, right? The red is the graph. That's the point z equals f of xy. Technically, the graph is the following set. Graph of f is x comma y comma f of xy, such that, well, x and y are real numbers here. Generally speaking, you'd limit to the domain of your level function. But the graph is a subset of R3, since we're dealing with a function of 2 variables. And, those red circles are just token parts of the graph, right? The real graph is formed from connecting all of those together, and this makes a what?
No code. Paraboloid, sorry.
Nathaniel, we got to get it together, man. Let's see here. So, that's okay. Yes, this is a what is it called? A paraboloid, right? Circular paraboloid, actually. So there's this interplay between contour plots and graphs, right? Which is better, the contour plot or the graph? You're like, we're modern students of mathematics. We don't make these kinds of value judgments of different object types, right? They each have their use. They each have their place. We believe in diversity. Very good. I'm glad you're an educated bunch. It's good. But that's actually the correct answer, because these have different points, right? Like if you want to visualize the function in 3 dimensions, this has certain advantages, right? For example, it's painfully obvious what the local minimum is in the graph, right? Over here, you can also see the local minimum, but it's not as sort of just in your face. The minimum's the vertex of the paraboloid, right? I mean, over here, you kind of have to look at it and go, wait a minute, there's kind of a trend here, right? And you can kind of sense that there's something funny going on at that point. So maybe that's a local max or min. Not that we've formally defined those yet. I'm just saying that's one of the things we're eventually going to talk about in here more properly. But these are really just two different ways of visualizing the same thing. Yeah.
Level curves are 2D while graphic.
Exactly, and that is the main point. The level curves are 2D, which means we can graph them pretty accurately, no matter how bad you are at. Like, there's only a few of us who can really bring this to life. Like, I can do simple ones, but if you get much more complicated, I'm up a creek. Yep.
So I know probably by definition it's not exactly this, but it's kind of like
It's okay.
a projection of
Uh-huh.
The three-dimensional shape.
Right. I think the
Shadow.
right. If we take a graph, so what you're asking me about is how to take a graph and to create the contour plot. So what you do is you take the graph and just like you're saying, you just slice it horizontally, chop, 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 and then the shadow of those onto the XY plane will give you the contours. Yeah.
You slice it into infinitely many slices.
Depends on how many contours you want to look at. Now, you're like, well, how many contours should we choose? How many contours should we choose? I chose you the contours for your homework. You notice how nice I was? I told you k equals -3, -2, -1, 0, 1, 2, 3. I took the decision work out of you. I mean, you didn't even have to decide how many is a good amount. I told you which k to do in your homework problem, you know? It's a service I provide. Also, I have learned over the years that if you just say, draw a contour plot on a test, there's just no telling what's going to happen. I mean, there's going to be some student who spends like a full 30 minutes to make 20 meticulously drawn contours, and there's going to be some other guys like, well, if I draw 2 curves, it's a plot, so he's probably not going to take off points, you know. So be careful with the instructions for these. Yeah. Anyway, so okay, great. What does the gradient have to do with any of this? How does the gradient figure in? How could we plot the gradient in these pictures? Which picture is really the appropriate place to plot the gradient? So the gradient, by definition here, guys, the gradient of f is equal to partial f, partial x, partial f, partial y. And so the gradient vector field, it lives in the domain, like it lives in the inputs for the function. It doesn't live really in the three-dimensional picture. The gradient's home is the contour plot. And in fact, for this function, what's the gradient actually? For this one, it's 2x, 2y. So if I try to plot those, right? Have I assigned this as homework? Curses. I mean, this is definitely an example in my notes. So even if I've assigned it as homework, it's still kind of like, you just look at the notes, right? So the point to this is if you pick any point here, the gradient looks something like this.
You gave us a much easier problem.
Oh, okay. Well, shame on me. Here. Should have made it impossible. I got a reputation to protect. Let's see here. Joking. You never know if your generation, whether sarcasm is understood. Let's see here. It's not really your generation. It's more depends on where you're from. If you're from up north, you're probably fine. I'm not saying that Southern people are intrinsically less valuable or worthwhile as people. I'm just saying that sometimes a certain kind of sarcasm is lost. I mean, Southerners have their own sarcasm, right? Which is, if you're a Northerner, you don't really understand it. Like when somebody says, bless her heart, that's really, I mean, that's biting criticism, really. These things you learn eventually. So the point is, this vector field, well, let me pick a specific point. So the gradient vector field, the other thing I'm not communicating yet to you guys effectively is that the gradient vector field we have to attach at the point we're evaluating it. So these are not based at the origin. These are based on the contours where we're talking about. So let's just pick a point. Let's say this point right here. right? That is, what is that point? I'm trying to pick 45 degrees on the level 9 contour. So that point is what? It's got the same x and y coordinates, and it's a distance 3 from the origin. Square root of 2. It's on the 3. It's on the 3. So I heard what I hear, 3 over root 2? 3 over root 2, I think that'll work. Because if you square that, you get 9 halves plus 9 halves, which is 9, which is saying it's on the level 3 curve, excuse me, the level 9 curve, which has radius 3, right? So yeah, that's 3 over root 2, 3 over root 2. And so what's the gradient look like there? Let me do it down here. Gradient of f at that point. What's that equal to? That's equal to 2 times 3 over root 2. Sorry, this contrast of x and y here is kind of hard to see because, well, anyway. So apparently that's, what is that? Just 3 square root of 2, 3 square root of 2. Now, these kind of pictures here, I really don't, this versus, say, this, I don't mean much different by it. I mean, I sometimes try to draw them so that the length is somewhat indicative of the magnitude, but not always. And depending on what mathematical software you use, the length of the vector fields and plots don't have much meaning. Mostly we're just after the direction with the picture, with the plots. If you do want to try to graph magnitude, I would suggest, slightly longer to illustrate where the magnitude is larger, shorter for where it's shorter. So, these should all have these brown ones out here should all have equal length if I'm doing it right, because they all have the same magnitude because it's just based on how far x, y is from the origin, right? Anyway, the larger point here is we plot the gradient vector field on the contour where it's attached, all right? That's where it goes. What does it mean? All right, so let's do a little calculation. Let's suppose that, let's see here. Suppose we got a level curve. Whee! All right, this is, let's say, f of xy equals to k, some level curve. And let's suppose that we have a parameterization of the level curve that goes through some point. Pick a point. How about this point right here? All right. Now I want to find a parameterization of the level curve. What does that mean in vector notation? We say, let's say t maps to r of t, all right? So that's a pair, right? It's a function of x for a function of time and y for a function of time, a parameterization of a curve in the plane. We say that that parameterizes C. Let me call this thing up here. Sometimes we'll just say like C colon, like that. That means C such that it's that level curve. This sentence right here is really just shorthand for saying C is equal to the inverse image of the set just containing k, which happens to be the same as x comma y, such that f of xy equals to k, for you math majors. So level curves are what are called inverse images. They're the set of all points which a given function maps to a particular thing, in this case, the constant k. Anyway, math jibber jabber aside, we say this parameterizes C if what? What we need is that f of r of t is equal to k for all t. Right? Now, sometimes you can't parameterize the whole curve, right? Like we've looked at things where maybe we parameterized like the left half of the hyperbola, but not the right half or something like that. Maybe there's some reason I can find a nice parameterization just for, say, just for this part, right? Maybe I just have a parameterization for this part in here, you know? So generally, parameterization is something we like to do locally. So I might say parameterize C provided this, and then we could add some, you know, through K, rather through P, you know. I'm sorry, my grammar is not awesome here. Moreover, assume that R of T naught is equal to P. I mean, I want to parameterize this C, and I guess I'm missing a word here, through P. I mean, again, you could have the case where you parameterize the whole curve, right? So this makes sense for the whole curve with respect to some choice of time. But maybe you can just do it just close to that one point, and that's still okay. It's still a parameterization. So anyway, larger point here. What is the relation geometrically between the parameterization and the gradient? Okay, so what we got to do is we got to take our equation, let me call it star. So you just take star, differentiate this thing. So what's the derivative with respect to time of f of r of t, right? That should be equal to the derivative with respect to time of the constant k. It's a constant k. What's its derivative? 0, right? None of us should have trouble with the right-hand side. The left-hand side I shared with you yesterday in a bit of a hurry. So let me say it again now calmly and slowly. There's a chain rule. All right? In advanced calculus or some course where the focus was more on analysis and less on applications, perhaps you'd prove this, but it can be proved that this is nothing more than the gradient of f at the point r of t, right, dotted with dr dt. So we have this condition, the gradient evaluated at the parameterization, all right, the gradient evaluated at the path which covers the curve, dotted with the velocity to that path, is 0. That means that the tangent line to the parameterization of the curve has to be perpendicular to the gradient vector because their dot product is 0. And in fact, this has to be true at all such t that the parameterization covers, right? So, you know, in particular, to get p, set what? We can set, you know, t equals to t naught to get the geometry at p. We get the gradient of f at r of t naught, right, dotted with dr dt at time t naught equals to 0. In other words, the gradient of f at the point P on the curve, dotted with, you know, r prime of t naught, if you will, well, that's equal to 0. So focusing in on my point P, if we draw the tangent line to the level curve, what's it look like? Like that, right? So the direction vector to that tangent line would be what I've called, you know, r prime of t naught, right? In what direction does the gradient vector point? Perpendicular. So without further information, I don't know if it points down or up in my picture. Right. Now, if I gave you another level, right, if I gave you another contour for this function, which I've not written the formula for, if I knew which way we were leveling up, if I knew which way the contours were going to increasing values, then I would be able to infer that the gradient went that direction. So for example, if I gave you extra information, if I said this blue given curve was, say, level 0, you know, and suppose I say that inside the blue curve there's, whee, something like that, and this is level -1, And then there's another level curve out here, which was level, 2. K equals to 2 down here. I should have done them different colors. I'll make the -1 dotted. And I'll make the level 2 multicolored and wiggly. There you go. It's a weird level curve. The point is, you could, well, I mean, it's not conclusive. It's not conclusive. We don't know for sure what else happens, but the odds are pretty good, given this situation, that the gradient must be pointing this way, because that's the direction in which we're leveling up, right? The given original curve was level 0, inside is level -1, so apparently the gradient must point like that. But this much we can generally say, the gradient has to point perpendicular to a given level surface, and it will point in the direction which we're leveling up, which is what we already saw here, actually, right? Any questions? So if I asked you to find, at a given point, for a given function, right, the direction in which you want to go to stay constant with respect to that function, what direction should you go? Perpendicular to the gradient, right? And in 2 dimensions, that's as easy as what I showed you last time. To get the perpendicular, you rotate by 90 degrees, right? If I have the vector, say, a comma b, if I just do, minus b comma a, this will be, or I can do what? B comma minus a. These are both perpendicular to AB. So which one you want depends on your application, but rotating a vector in 2 dimensions is not a big deal. 90 degrees at least. Take a breath here. Any questions? So, talk a second here about, well, let me talk more about a particular application. Yeah?
Did I miss something over there?
Like what?
The bottom right.
Bottom right?
No. The middle. Whatever gradient is.
This?
Yeah.
What I'm doing here is I'm working out the specific details of what the gradient vector is at that one point. That's all. Because I drew all these gray, brown arrows. I didn't explain to you how I got them. How I get these specifically is plugging in those points into this formula. And so, like, for example, the point 3 over root 2, 3 over root 2, if you plug that into the gradient formula, we get that.
Is that the simplification of it?
Oh, this?
Yeah.
Yes. 2 over root 2 is root 2. Ah. Is that what we're asking about? Ah. I see. So the other big application for gradients, in my view, would be the non-Cartesian coordinate systems. So for the plane, what's our choice? We did what? We did x equals to r cosine theta, right? We did y is equal to r sine theta. So I pointed out that, of course, you have, let's see here, r is equal to the square root of x squared plus y squared, right? So that says that the gradient of r, right? The gradient of r is what? It's partial r, partial x, partial r, partial y. But you remember the daily quiz we did, like 2 days ago or whenever. think it fell on Nathaniel, I think. And we worked out that that's actually x over r, and that's y over r, right? Now, if you want to recast that in terms of purely polar coordinates, what is that? What is x over r and what's y over r? X over r is cosine theta, y over r is what? Sine theta, right? And so apparently, the gradient of r is cosine theta, sine theta in terms of polar coordinates. This is such an important quantity, I give it another name. I call this r hat. And the reason for that is very simple, because it points in the direction in which r levels up. It's obvious as I write it in sine and cosine that it's a unit vector, right? And so we can, what's the level curve of r look like? This is a level curve of r, right? What's r hat look like? It's just the radially outward vector field, right? Like this. This is r hat. I've just drawn it 4 places. Of course, you could draw it at any point in the plane, except maybe one. There's one place where r hat's not a good citizen of the mathematical world. Where's that? What's that? The origin. Yeah, origin is very troubling because that's where we get division by 0, which is not nice. Polar coordinates, strictly speaking, break down at the origin. On the other hand, we could look at theta. What's theta equal to? Well, let's focus on quadrants 1 and 4, where I have a nice formula. But you notice that if we are anywhere else, the theta is still given by the inverse tangent of y over x, right? I mean, technically speaking, depending on where you are, you might have to add pi or something, right? So the derivatives are the same all the way around, even though the formula changes in quadrants 2 and 3. Right? I mean, I could say plus some constant, where that constant is really not a constant. I mean, it's not a constant. It's different in different sectors, right? But setting aside the coordinate axes, that's either 0 or pi. The point is, when you differentiate it, this thing goes away. So let me stop talking about that. What's the gradient of theta? So that would be what? Partial x of inverse tangent of y over x, right? And partial y of inverse tangent, excuse me, of y over x. Let's see here. So we have to differentiate the inverse tangent. So that gives us 1 over 1 plus y squared over x squared, partial x of y over x. And then we get 1 over 1 plus y squared over x squared. Chain rule, partial x. I'm sorry, y, right? Partial y of y over x. Now, the inside derivative is much easier on the second component than the first, right? I mean, the second component, that differentiates to 1 over x, right? The first component differentiates to minus y over x squared. So we got what? We got minus y over x squared times 1 plus y squared over x squared, right? Comma. And here we get 1 over x times 1 plus y squared over x squared, right? So what you got to do here is use your imagination, multiply this one by x over x. See why I do that? I mean, I do that so that I get an x squared in the denominator, which clears out the y squared over x squared, and we get the nice following, pretty nice formula. Minus y over x squared plus y squared, right? And this is x over x squared plus y squared. Now, can you guys tell me how to rewrite that? How can we rewrite that in terms of polar coordinates? So you're still the gradient of theta. I'll write it again here, guys. So you said I've got, let me just, I'm not doing anything. I'm just copying it down again at the moment. Now you guys tell me what to do next. What do you want to do? What's your next move? How about the denominator is r squared, right? So we've got minus y over r squared and x over r squared. But y over r is sine theta, right? X over r is cosine theta, right? And we just got an extra 1 over r. So those simplify to, what is that? That minus sine theta over r and cosine theta over r, right? Of course, we can simplify that. The gradient of theta is 1 over r minus sine theta cosine theta, right? So is that a unit vector? Well, no, right? What's the length of the gradient of theta? Yeah, it's 1 over r. So if I want to define a unit vector in the direction of increasing theta, in the direction in which theta levels up, what should I do? I just have to normalize it, right? So this tells me that theta hat is going to be defined as the gradient of theta divided by the length of the gradient of theta, and that is nothing more than this unit vector sitting up there, minus sine theta, comma cosine theta. There is your beloved, well, beloved to me. It doesn't have to be beloved to you, but that's theta hat. And that points perpendicular to the level curves of theta. What are the level curves of theta? Let me draw some of these theta hats here in red. What's r hat dot theta hat? Yeah, r hat dot theta hat 0. They are perpendicular, right? If you pick another point in between here, say like this one, right here, at angle theta, right? We've still got what r hat points out like that, right? And where's theta hat go? Like this, right? What are the level curves of theta? What are the theta contours in this picture, so to speak? They're just rays, right? These are the theta level curves. They're just lines. Well, they're not lines, they're rays, right? When I tell you theta equals to pi over 3, right? For example, theta equals to pi over 3, because of our definition in here, is this, right? Why? What? You know, because in here I insist that the radius is positive, yeah? See that? There's no plus minus here. So that thing we do in Calculus 2 with reflecting through the origin for negative radius, I don't do here. So when I say theta equals pi over 3, I'm talking about a ray from the origin out like that. If I want the other half of the line, this guy down here, what would this be? Yeah, 4 pi over 3. Right. So this is r hat and theta hat in a nutshell, and it's just, again, another application of the gradient idea. You just have to calculate the gradient of your curvilinear function and normalize it to length 1. That gives you the unit vectors in the direction in which those curvilinear functions increase. In this case, r hat and theta hat. So it's pretty neat. It also is a nice language, see, because this thing right back here, we could rewrite in terms of polar coordinates in a more elegant way. This is really nothing more than 2 times the square root of x squared. Well, here, let me put it in the polar coordinates just directly. Let me not do something weird. What's x in polar coordinates? R cosine theta. This is r sine theta. 2r sine theta, right? So we can factor the 2r out, and we got cosine theta sine theta, which is what? This is 2r r hat. And you see this formula for the gradient of f is beautiful. 2r r hat. That tells me everything I need to know. It tells me that this vector field points in the radially outward direction, and then its magnitude is twice the radius wherever you are. I would argue that that's better than the xy formula. It's more clear geometrically what that is. And that's part of the reason that I introduced non-Cartesian coordinate systems, is because they allow us a more clean discussion of vector fields which happen to have a circular symmetry. Why should you care about vector fields with a circular symmetry? How about physics, right? We're all the time coming across things that have a circular pattern in physics, and so it's nice to know about polar coordinates. All right. Let me do another example. Oh, I can't use this. That's the bad thing, is once you use water and a paper towel, you have to keep using it because nothing else will erase after that point. Here, let me do an example which is a little bit ickier. So here's an example. Suppose we have f of xy equal to 3x squared minus e to the xy, right? Let's find parameterization of tangent line and normal line to the point, let's see here, now I got to think of a point. Let's see. Oh, I can pick any point. How about 1, 2 on the level curve? What level curve is that? How do I figure out, if I tell you that 1, 2 is in a level curve of f, it's in a contour of f, how do I find which level that is? Yeah, just plug in that point. So the level curve is 3x squared minus e to the xy equals to what? Yeah, 3 minus e squared, yeah. Okay, yeah, great. So there's the question. So before I even do any calculations, let's just draw a symbolic picture of what's going on. We'll call this point, here's my point, 1, 2, right? The level curve, I don't really even care. It looks something, maybe it looks like this. I'm not sure exactly what it is, but it goes through that point by construction, right? This is the 3x squared minus e to the xy equals to 3 minus e squared curve, right? So I know the normal line. What's the normal line look like? This is my normal line, right? The normal line, by definition, lines up with the gradient, okay? I'm assuming the gradient's non-zero in that definition. And how about the tangent line? Well, the tangent line, it follows the tangent to the curve, right? Now, if you already have a parameterization to the curve, finding the tangent line is easy, right? You have a parameterized curve. How do you find the tangent line? You differentiate. You don't bother plugging in the point, and you just write it down, right? Sorry, I'll get over it eventually. You differentiate. You plug in the point. That's the velocity vector, which is the direction vector for your tangent line, right? What's the parameterization for this curve? You could find one, maybe, but we don't have it, do we? But that doesn't matter because we can figure out what the tangent line is by geometry alone. We don't need the parameterization because we know that the tangent line is perpendicular to the normal line, and we know we can calculate the direction vector to the normal line from the gradient, right? And then we can use our 2D rotation idea to pick up the tangent line, no problem. So let's get to work. What's the gradient? Nabla. Nabla f. This is nabla, by the way. Nabla. All right, so the nabla at an arbitrary point, the gradient, is, looks like we got ourselves a 6x minus y e to the xy, comma, 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 comma. Partial differentiate e to the xy. Let me just write over here. Partial y e to the xy. How do we think about that? That is e to the xy partial y of xy by the chain rule, right? And so that just works out to x. So we have x e to the xy. Oh yeah, there's that minus there. Don't forget that. Thank you. Now, this, to be more pedantic, this is really the gradient vector field where? At the point x comma y, right? I don't usually write that evaluation, but technically, yeah. So, what's the gradient vector field? What's the gradient vector, rather, at the specific point 1, 2? We just have to plug in x equals to 1 and y equals to 2 and see what comes out, right? So we get ourselves a 6 minus 2e squared, and then we got ourselves a minus e squared, yeah? So that is a direction vector for the normal line. So therefore, parameterize the normal line, right? Let's say R1 of t is equal to 1 comma 2, because that's my base point, plus t times this guy. 6 minus 2e squared, comma, minus e squared. There you go. That is a parameterization for the normal line. How about the tangent line? How do we parameterize the tangent line? Let's say R2 of t. Base point, still 1, 2, right? What's the direction vector I use? It shows e squared, which means you now have committed to 6 minus 2e squared for the second component, right? If you did it right, the dot product of the direction vectors of the normal and the tangent line should be 0, right? And indeed, they are, yeah. So we're just using flip components and multiply one of them by minus. Do not flip components and multiply both of them by minus, then you would be wrong. A popular mistake for half-understanding students. Yeah. But that's not most of you guys. Again, you guys did pretty well in the first test. I've been warned to not praise you too much because then you'll be like, I can slack off. I don't really see that's going to happen, though. I don't think you guys realize that this class is not a sprint, it's a marathon, right? I mean, it goes on and on. This is a 4-hour calculus class. It's nearly endless, right? It's pretty amazing, really, because it's math, you know? I sometimes forget to tell you guys, but I really do love teaching math. It's really pretty much the only way in life that I can gather together a room full of people and talk to them about math for more than like 30 seconds and not have them walk away. Oh, and I get paid for it. So it's not bad, really. But I should hold this more secretly, because if the administration hears, they might get the idea that they don't need to pay me as much if they found out that I enjoyed it as much as I do. Don't tell them. Don't tell them. Okay, so does this make sense? I hope. Maybe. So let's take the remaining 10 minutes to look at some pictures, and I want to share with you some sort of more pathological features of what we're doing. So I keep mentioning that, you know, there's this thing called continuous differentiability, right? And so I'd like to try to talk to you a little bit more about what is continuous differentiability, why do we need it, and what's that all about. This leads us into the more general discussion of what I call the general derivative. The general derivative, so, you know, we calculate these partial derivatives, you know, and for a function of two variables, you can get a sense of what it is, you know. There's this nice cut and dried interpretation. Partial derivatives give us the fixed rate of change of the function in a particular direction, right? So the tie-in with partial derivatives and directional derivatives is very nice for functions that are real valued functions of several variables. But as you go on in this course, you'll see that we use, go away, this annoying little thing I can't get, Windows 10. But what you said about the forced updates in the Mac, it makes me feel better about my life. Like, it's not just, I'm not the only one. Come on, tell me oh man. I got money. It's not helping. I'm looking for my, none of you happen to have a USB to VGA adapter just on you? And none of you work for some sort of like museum of technology or something?
My laptop does have a VGA port, so
It does have a VGA. Your laptop has a VGA port? And you have notes on it?
Yes.
All right, I'll take you up on that. This is very frustrating because I have a distinct memory of, so if you can load up the notes. I have a distinct memory of pulling that VGA to USB, or whatever it is, HDMI rather, thing out, and then putting it back in my bag. So why is it not in there now? It's very disturbing. So here's the thing we'll be talking about here momentarily. So suppose, you know, we've got this function, right? Talk about two dimensions for a second. So here's a point, right? And you can calculate sort of these, you know, if you feed points, you feed the lines that go through the point down here, right? This point would be P, and the slopes of these, in some sense, describe the directional derivative u hat f at P, right? If we were to, you know, just cut this vertically in the vertical slice, the slope in that trace of the graph is the directional derivative, right? But the thing that's really weird is it is possible. Thank you.
You have to use the track point, though. We don't like the track point.
You know, beggars can't be choosers.